Hello everybody, this is Scott Darmus. It turns out that my original method of calculating p-values is still more valid than the new idea I had yesterday or the day before yesterday. So this is the original method. Basically what I was doing and what still seems to be the right approach is to treat every hierarchy assessment for each element like a type of Bernoulli trial. And so you would say, okay, you have A on top, and what is the chance that all of the others which are predicted to be below actually are below? And so that chance would be times a half, so that then you get a score here. But then you would want to assess the probability for relative to all the elements. But then you cannot multiply those probabilities because those are not independent probabilities. The way you deal with it is by making these scores here. Like here, the perfect agreement here would be is already this 0.125. Sorry, I clicked somewhere. Let's go back up here. So so you create this these scores here, and then you subtract them from the total number. Like in this case, it's 3. 3 minus 2 is 1, subtracted 1. So then you have 1 over n factorial. And that's how you calculate it. So this original method is quite good because it introduces probabilities from the get-go. It doesn't try to jump to factorials immediately. The new method that I was trying out, it seemed to have where is it? Yeah, so this is the new approach, which had excellent agreement for n equals 2, a perfect agreement, and also much better for n equals 3. Like when you compare it with the original one, it looks not so good because there's a gap here. But actually it's better because the shape is the same. So the new approach seemed like it's kind of better, but it was not really. And when you go over to n equals 4, then it kind of starts falling apart a bit. You see that here. Well, yesterday I said this kind of looks good because the lines have a similar shape, kind of, but you already see that it's kind of too flat. And in the old one, it looked like this. It's kind of more pronounced. And n equals 5, yeah, it was also more pronounced, going up in the middle. But with the new approach. With the new approach, you can see that, where is it? One moment, here's the picture. You can see it's like totally flat. So the new approach is not the right thing to do. The original approach is much better. Basically, I tried out that new approach because I felt like the score for the factorials, fractional factorials, I thought it should sort of reflect, like if it's like 50% agreement, sort of, it should be like a score of a half instead of having these very small scores at times where they come from Bernoulli trials. So the original scores were sort of like pseudo probabilities. and so sometimes there would be quite small numbers. But it turns out that that's the right approach. Basically, you calculate probabilities based on, okay, what's the chance that all these are predicted to be low, and they are lower, and like if it was random, then it would be like a 50% chance, and then you compensate for the fact that you're not supposed to multiply probabilities that are not independent. You compensate for that by creating these scores and subtracting. Yeah. So that's the right approach, and that's the approach I've been using in the past 1.5 years. So that's better than the new approach that I introduced yesterday. But it's interesting that the new approach was giving better results for the very low cases, n equals 2 and 3. Yeah, sort of better, but yeah, not really. You cannot only look at the how much deviation there is. Like sometimes the shape is more important. Yeah. So, but to really know how well this method really works is you would have to use programming to probe it for higher values of n, like n equals 6, 7, 8, 10, yeah, and higher. But for what's relevant to my theory, SPD chromogravity, we can basically also just use the normal approximation. One moment, here's this is the graph that proves my theory to be correct. You can see the different measurements of the gravitational constant, which is not a constant. And basically my formula says that the chance that this is a coincidence is 1 in 10 to the power of 13. So yeah, the normal approximation should yield the same. And here I already prepared Kendall's tau here. So today I'm going to start calculating this p-value for with the normal approximation. Let's see what will come out. Okay.